following video will introduce the concept of elastic and inelastic collisions, including formulas for calculating the initial and final velocities of objects involved in different types of collisions, and then concluding with a real-world example of how the lesson content can be applied to real-life systems. The concept explained in this presentation is from Chapter 5.3, which covers collisions, from the second unit, which covers energy and momentum-related topics. There are two types of collisions in physics systems, and they are elastic and inelastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. Objects will bounce off of each other. An example of an elastic collision is curling, where two curling stones are hit against each other on the ice, and they bounce off each other. There is also a perfectly elastic collision, in which mass and velocity values can be solved for using the following formula. The other type of collision is an inelastic collision, where only momentum is conserved, and kinetic energy may be transformed into other forms of energy. Mass and velocity values can also be solved for in a perfectly inelastic collision using the following formula. Now let's try an example question. A 2 kg collision cart traveling at 5.5 meters per second east collides with a 1.5 kg collision cart traveling at 0.5 meters per second east. The carts bounce off each other. If cart 1 travels at 1 meter per second after the collision, calculate the speed of cart 2 after the collision. First, I start by writing down the given values. We're given mass 1, mass 2, the initial velocities of the first and second cart, and the final velocity of only cart number 1. We then use the perfectly elastic formula, as the question says that the carts bounce off of each other, which happens in an elastic collision, and we rearrange it to solve for the final velocity of cart number 2, which, after doing the calculations, adds up to be 6.5 meters per second east. But how do these collisions relate in our daily lives? In order to look at that, we have to look at something like cars, for example. As technology continues to evolve, cars become safer and safer. Many safety features have been invented over the years, such as blind spot detection, airbags, crumple zones. Wait, what's a crumple zone? A crumple zone is the front or rear section of a car that has been purposely engineered to be weaker than the rest of the car. In a crash, these zones are designed to crumple and absorb most of the energy acting on the car. Crumple zones are designed to increase the amount of time that the force acts on a car in a collision. This makes the total kinetic energy during a crash decrease as it is absorbed by the crumple zone and isn't completely exerted on vehicle occupants. If a crash was completely elastic, the passengers would have large amounts of kinetic force exerted on them. In the following video, a 2009 Chevy Malibu collides with a 1959 Chevy Bel Air. The two cars are traveling at the same speed, yet the older of the two is damaged much more. Notice how its passenger cabin crumples, just like the front of it, while the newer car's front crumples, but the rigid passenger cabin remains mostly intact. Because the older car doesn't have a crumple zone, all the energy from the crash is directed throughout the entire vehicle, resulting in a lower survival rate for passengers inside. The newer car's crumple zone works to absorb the initial crash energy and keeps its occupants safer. But can this be demonstrated using a real experiment? This is a toy car, made completely out of solid metal. It has no crumple zones, and when pushed into a solid wall, it will bounce off in an elastic collision. I have glued a spring with a ball to the car roof to show the transfer of energy during the initial collision. The car is pushed backwards and thrown forwards, and as you can see, after impact, the spring violently jerks due to the kinetic force acting on the car traveling throughout its entire structure. Now I will repeat the experiment, but this time I will attach some plastic to the front of the car to act as a crumple zone. When the experiment is repeated and the car is a crumple zone, as you can see, the spring doesn't move as much as it did before. This is because energy is absorbed by the crumple zone, and not as much energy is transferred to the vehicle occupants, or in this case, the spring. Crumple zones in modern-day cars reduce the elasticity in a head-on collision, which in turn decrease the amount of kinetic energy acting on each car and prevent as much energy from being exerted on vehicle occupants as possible. This accounts for a safer ride and is one of the many examples of how physics systems are a part of our daily lives. Thank you for watching.